I'm going to prove pi is irrational. First, I'm going to prove these lemmas. Proof by contradiction. So we're going to assume that pi is rational. Later, we're going to reach some contradiction. So first of all, left-hand side of this equation is equal to n factorial and a over b minus x quantity to the power of n. That's replacing x with this value. Also times a minus b times likewise a over b minus x all together to the power of n, and that is equal to n factorial. Common denominator here is b. At the top we have a minus bx. Then we just distribute the power to the top and bottom. And we have to deal with this. So b times a over b, that's a. A minus a, 0. And minus b times minus x, that's bx. And again, we distribute the power. B to the power of n, x to the power of n. And b to the power n, b to the power n, just cancel out. That is equal to n factorial. We have a minus bx, quantity to the power of n times x to the power of n. That is indeed f of x, indeed equal to the right-hand side. So the first lemma is proven. And the second lemma, the kth order derivative. So the kth order derivative is equal to the sum from 0 to k, 1 over n factorial. This is a constant. It has nothing to do with I or anything. And we have a combination number. K, choose I, according to the formula. And then we have x to the power of n. Take the ith order derivative. Then we have a minus bx, quantity to the power of n. Then we take its k minus ith order derivative. Because we have the formula where if we have a product of two functions, this function times that function, we have the formula that's pretty much like the binomial expansion where we have some combination number, right? As in binomial expansion, we have the power, but in this case, we have the order of derivative. So this is fine. Like, we want to rewrite it into more details, into 0 from k, 1 over n factorial, k choose I, and I'm going to derive this one. Right? So n times n minus 1, all the way down to n minus I plus 1, times x to the power of n minus I. So this pattern is clear. So each time we take its derivative, the power just keep reducing by 1. And we just take down the power to the front, take down the power to the front. This is eventually what we have. It's a clear pattern. And just copy down the remaining. So a minus bx to the power of n. Take the k minus ith order. So in this case, I want to restrict k between 0 and 2n. And I have to discuss case number 1, where k is larger than or equal to 0 and less than or equal to n minus 1. In this case, k is relatively small. So I goes from 0 up to k. So in other words, I can no larger than n minus 1, right? The maximum value of I is just n minus 1. So in this case, n minus I, so in the worst case scenario, I just have n minus bracket n minus 1. That's the worst case scenario. But even in that case, I still have a power of just 1. For other i's in this case, the power is always positive integer. So all in all, in this sum, every single term will contain this factor, that is x to the power of positive integer. So when I let x equal to 0, then I just have sum of zeros, right? Which is also equal to 0. Goes from 0 to k. It's really equal to 0. That is also equal to the left-hand side. That is f kth order derivative at 0. So this really an integer in this case. Now, case number 2, where k is equal to n in this case. First, I'm going to look at the partial sum, where, of course, I'm going to look at x equal to 0. In this case, my partial sum is from 0 all the way up to n minus 1. Now, this equation is true when k is restricted in this restriction. So in other words, even if k is equal to n minus 1, my sum is still equal to 0 when x is equal to 0. Right, so it goes from 0 to n minus 1, still equal to 0, right, in this case. And my final term, that is when I equals n, right, because this partial term, this is my final term, altogether they just make up the entire sum. So this single term is equal to what? So when I is equal to n, so n minus n power of 0. So this will turn into 1. So we have n minus n plus 1, right? This will become 1. So n times n minus 1 all the way down to 1. So this will turn into n factorial. And we have 1 over n factorial. They just multiply to become 1. And this combination number is also some integer. So all in all, this up to this will multiply to give us some integer. How about this term? K minus I, right? K is n, I is n. This becomes 0th order derivative, meaning just this term itself. So when x equal to 0, this will become what? A to the power of n, also some integer. Right? So again, here that doesn't matter because here I no longer have x, right? So this already is an integer. This also an integer. So all in all, this is also some integer. So partial sum integer, the final term some integer. So all in all, altogether, the sum from 0 all the way up to k, right? That is n, is indeed some integer, right? In other words, that is also, equal to the left-hand side when kth order derivative at 0 is really some integer. So case number 3, when k is larger than or equal to n plus 1 and less than or equal to 2n, in this case, still I'm going to look at the partial sum. Partial sum from 0 all the way up to n. This is fine because k is minimum n plus 1. So it's okay for me to just look at this partial sum, just only up to n. Like I said, in case number 2, I've proven that when it's sum from 0 to n, then it's some integer, right? And also, what's the remaining sum? That is from n plus 1 all the way up to k. Now, in this case, minimum value is n plus 1. Let's look at this order. Right? So minimum is n plus 1. So the order of derivative is already strictly bigger than the power. Power is some positive integer. So in this case, obviously, as we repetitively take its derivative, and in the end, we will just make it turn into 0, right? That is obvious. So this will already turn into 0. So I don't even care about this term. Right? So 0 times also becomes 0. And doesn't even matter. Of course, here we just, again, we will first let x equal to 0. And this is some integer. In this case, we're going to have 0, right? All zeros. Zeros, the sum of zeros is also equal to 0. Right? Doesn't matter if x is equal to 0 or not. But so all in all, when x is equal to 0, my partial sum plus my remaining sum, all in all, my entire sum from 0 all the way up to k is indeed some integer. And in other words, this is indeed my left-hand side. F kth order derivative at 0 is indeed some integer. So all in all, when k is in between 0 and 2k and 2n, kth order derivative of at 0 is indeed some integer. And how about when x is equal to a over b? Right? This is also an integer, because the first lemma tells us that if we take the kth order derivative on both sides, they should also equal to each other. And after that, we just replace x with 0. So in the end, we have kth order derivative at 0 is equal to kth order derivative at a over b. Right? So I've shown that kth order derivative at 0 is some integer. And this is equal to that, right, deriving from this. So in other words, the kth order derivative at a over b is also some integer. So this is proven and this is proven. Now I'm going to prove the third lemma. Now I'm done with the first lemma and second lemma. So the third lemma, the integral, how can it be some integer? So here's the reason. So following our assumption, so the integral from 0 to pi f of x sine x dx. So why is it an integer? So first of all, we can use integral by parts. So in this case, f of x is u, sine x dx is dv. The v is minus cosine x. Now, that is equal to u times v. From 0 to pi minus 0 to pi. v times du, v times du. What's du? U is f, du is f dash. Right? U dv, v du, minus cosine x. Minus cosine x. So minus sine. Minus minus, that's minus to the power of 2. Right? So we have plus minus 1 to the power of 2. That's the pattern. Now, if we replace x with pi and x with 0, right? What's going to happen is that, remember, the kth order derivative, k, even if it's equal to 0, that's the 0th order derivative. That's doing nothing, right? Function itself, right? Derivative is always integer at those 2 points, right? Pi is equal to a over b, same a, same b. So cosine x, cosine pi, cosine 0, of course, integers. So in this case, this is really some integer. We can rewrite it into some integer m1 plus minus 1 to the power 2 times this integral. This integral, I'm going to again use integral by parts. Right? U times dv. What's v? V is sine x. Right? So again, f dash x times sine x from 0 to pi minus 0 to pi uv, v times du. Du is f double dash v sine x. Now, let's look at this term, right? For the same reason, lemma number 2, right? Kth order derivative at those 2 points is always some integer. Again, sine pi, sine 0, integer as well. So again, this is an integer times negative 1 to the power of 2. Still some integer. Integer time plus some integer. Still an integer. So integer m2 minus to the power of 2 times minus 1 minus 1 to the power of 3 times integral from 0 to pi f double dash sine x dx. We just repetitively use integral by parts. In the end, we should have something like, until we reach the 2nth order derivative in here, right? What's the pattern? m sub 2n, right? Some integer, whatever, positive, negative, plus minus 1 to the power of, what's the pattern here? The power should be exactly 1 unit larger than the, in this case, 2n plus 1 times integral from 0 to pi f the 2nth order derivative. Is it sine x or cosine x? When the order is even, it's sine x. Yes, it's sine x. Now, in this case, let's look at the 2nth order derivative. I claim it is an integer. The reason is because the degree of f is exactly 2n, right? Then the 2nth order derivative will make our function turn into some constant, right? And this constant has nothing to do with x. And not only that, I also know that from lemma 2, the 2nth order derivative is some integer at those 2 points. But like I said, the 2 nth order derivative is already some constant that has nothing to do with x. And so that constant has to be some integer, right? So this has to be some integer as well. Constant, that's also an integer. So again, overall, we have some integer plus some integer times some integer. Take this integer out here. Integrate from 0 to pi sine x dx. That is essentially also some, because antiderivative of sine minus cosine x evaluated from 0 to pi. Also some integer. Integer, so in the end we have some integer. Right? Now I'm done with the first and second and third lemma. So, first of all, this integral is some integer. Then I'm going to show that this integral is strictly larger than, I'm not going to prove it, but I'm going to use the fact, I'll prove it in a future video. This fact that if some function g is continuous over some closed interval, and also if g is non-negative, and also there is some point where the function value is strictly positive. X is in this interval. Then we can conclude that the integral from a to b of g is strictly positive. So in other words, as long as g is continuous over this interval and g is not consistently 0 but non-negative, right? There's at least one point where it's larger than 0. Then we can show. I'm going to prove it in a future video. And we can easily establish that f of x times sine x easily satisfies these conditions, easily verifiable. Therefore, the integral of this thing is easily just strictly larger than 0. This is when n is fixed. Because even though the integral is some integer, but that integer has something to do with n. It's like a sequence of n. So this is when n is fixed. Indeed, strictly larger than 0. I'll prove that in a future video. At the same time, it's some integer. So an integer that's strictly larger than 0. So that is larger than or equal to 1. Right? Sine x dx. At the same time, it's going to be less than or equal to some other things. So I'm going to loosen f of x a little bit. I'm going to loosen, because first of all, f of x can be written as, first of all, I'm going to write down n factorial. And I'm going to write down, first of all, x times a minus bx altogether to the power of n. Then I'm going to rewrite it into I'm going to multiply by b and divide by b. Right? Divide by b, multiply by b, bx times a minus bx. Altogether, raised to the power of n. In this case, I'm going to look at just bx times a minus bx. First of all, we can easily verify that bx is larger than or equal to 0. And a minus bx is also larger than or equal to 0. Given that x is in this interval 0 to pi, 0 to a over b, right? So we have two real numbers that are both positive or non-negative. In other words, we can use the AM-GM inequality, right? Less than or equal to half of the sum of bx plus a minus bx. We altogether square. That's the AM-GM inequality. So this becomes 4a squared. So it can be no larger than this value. So f of x can be no larger than fx can be no larger than, if we replace this with that, right? 4a squared, 4 times b, n factorial, 1 over n factorial. Then we have 4b a squared altogether to the power of n. Right. F of x, at the same time, it's non-negative. It can be easily proven to be non-negative in this interval. Non-negative. In this case, I can easily show that replace f of x with this constant, further loosen this inequality, right? So 1 is less than or equal to integral from 0 to pi f of x sine x dx. First of all, maybe I want to replace sine x with just 1. Right? Sine x in this region is between 0 and 1. If I replace sine x with 1, it's further loosened. I also replace f of x with this value, also further loosened. Therefore, it's less than or equal to, first of all, replace f with this value, take out the constant, and sine x replace 1. So integral from 0 to pi, 1 dx. That's just pi, right? Pi times this constant, right? Pi times this constant. That is just a over b times this constant, a squared over 4b power n. Now, I've proved in a previous video that the limit of this sequence is equal to 0. Because 1 over n factorial times some constant to the power of n, this limit is equal to 0 as n approaches infinity. I will include the link of my video. So, times some constant, still approaching 0. Right, still approaching 0. So first of all, since I'm going to use the definition of the limit, right? So first of all, the definition of the for any epsilon, right? For any epsilon, I'm going to choose a special epsilon. That's b over a times half. Right, half b over a. Right. Larger than 0. There exists some capital N, as long as little n is larger than capital N, the absolute value of this sequence minus 0 is small enough. In other words, I don't even need the absolute value because it's already positive. Right? Already positive. This will be already positive. Right? Can be small enough, smaller than my epsilon. Right? B over A times half. So I'm gonna fix some n naught. N naught that's larger than capital N. It says for any small n that's large enough, larger than the fixed capital N, this inequality is true. Therefore, I just fix some n naught larger than the capital N. It should also remain true. Right, should also be true. Therefore, I say n is fixed. This inequality is true. Right? So in other words, if n is fixed to be n naught, this inequality is always true, also true. Right? Just replace. So again, 1 is 0 to pi, less than or equal to. This is when n is fixed to be n naught. So n naught. And so n naught factorial n naught inequality also true, right? Replaced with that. B over A times half. That is half. So we have the integral proven to be some integer. And this integer is not only larger than or equal to 1, but also less than or equal to half, which is entirely impossible. So therefore, really, my assumption is false. Therefore, pi is really irrational.